So in the last class, basically, we introduced the concept of the Parkes transformation with the target to actually have the independency of the inductance matrices over with respect to time or with respect to position. So this was the basic target why we actually introduced the Parkes transformation matrix. And we went through some example or application of Parkes transformation for converting between ABC frame and DQ0 frame. So we started with the current transformation, and then we used up some of the current and voltage relationships between the ABC and DQ frame to calculate or to obtain the apparent power expression. And we saw that, well, depending on the choices of these K1 and K2 parameters, which are present in the T matrix here, we can end up with some different conclusions. Like if we take a set of K1 and K2 values, then we might come up with power invariant transformation. If we use another set of K1 and K2, then we might not end up with the power invariant transformation, but we might end up with some other useful relationship between the peak values of voltages and or currents, where they are similar or they are same, they remain same in each system, in each transformed system. And then we applied the Parkes transformation for the stator winding voltage equations, and we obtained, we are supposed to obtain the VD, VQ, and V0. Of course, there are some steps skipped from this long derivation, and those are supposed to be solved from your end as a part of the assignment number 1. Okay. So let's continue from here today. So we have the stator winding voltage equations, and now this is in matrix form. So if you break down these expressions and write in simpler form, so we will get from these 3 equations, VD, VQ, and V0, we can simply write them as simple equations. Like VD would be what? So VD would be, if I go through this line, so VD would be simply, there is a minus sign, then minus RS ID and minus omega lambda Q plus d lambda d over dt. This would be our VD. And VQ would be minus RS IQ omega lambda d plus d lambda Q over dt. And V0 would be simply minus RS I0 plus, there would be no second term here out of this matrix because all will be 0, and then d lambda 0 by dt. So these VD, VQ, and V0, remember, these 3 are actually the outcome of applying some Parkes transformation matrix over our ABC reference frame voltages. Okay. And these ABC reference frame voltages are actually linked up with the stator coils. Okay, stator coils. Once we come into the DQ0 reference frame, then as we know, the D axis and Q axis, they are actually aligned, or specifically the D axis, it is actually aligned along the rotor main field axis. So by this transformation, another way to say that, another way to explain that we were actually in the stationary frame. So the stator is basically our stationary frame. So we were in the stationary frame, and by transforming with the help of the Parkes transformation matrix, we are moving into some rotating reference frame. Okay. So another way to look into the Parkes transformation application is that we are transforming the variables which were originally in the stationary frame and 3-phase stationary frame, and we are transforming into another 3 coordinates which are rotating, which are in the rotating frame. So for synchronous machine, it is always an advantage, added advantage, if we take this rotational speed equal to the synchronous speed, so that at least in the steady state case, steady state operation, we have some fixed constant DC values Okay, we don't have the like these VA, VB, VC. They are some sine function of omega t. Okay, sine omega t plus theta, sine omega t minus theta, some sort of that, sine or cosine. So they are time dependent. Okay, in the stationary frame, these VA, VB, and VC, they are time dependent. Whereas in the rotating frame, these VD, VQ, and V0, they would give me simply some DC values. So we end up with these equations 8A, B, and C out of the matrix for the stator voltages. And what about the rotor quantities? Remember the rotor voltages we wrote down earlier. So if we go back for the rotor winding voltages, the rotor flux linkage, so these are the rotor winding voltages. Now, in which frame they are? Can anyone mention? Are they in the stationary frame or in some different frames? These 4 voltages.
Rotating frame.
They are already in the rotating frame. Remember the location of the field winding? The field winding was present along the D axis. Okay. 1D is the damper winding, again placed either physically present or hypothetically modeled damper winding effect. So this is also along the D axis. 1Q and 2Q, these were along the Q axis. So there is a difference. While we are applying the transformation, we have to know actually which quantities we have to transform using the Parkes transformation. So as I said, the stator winding voltages, they are staying, they were in the ABC stationary reference frame. That's why we required to apply the Parkes transformation on them. On the other hand, the rotor winding voltages, they are already along either the D axis or the Q axis. That means they are already along the rotating reference frame. So we don't have to bother about applying any sort of transformation on these 4 voltages. Okay. So with that information, we actually keep whatever expressions we earlier had for these 4 rotor winding voltages, VFD, V1D, V1Q, and V2Q. And again, as mentioned earlier, because all these currents that we see here on the right-hand side of these 4 expressions, all these currents, they are having a positive direction. On the other hand, the currents present in the DQ0 reference frame, even after transformation, you see that they are having a minus sign. So now we have actually all the voltages, the stator winding voltages, the rotor winding voltages, all are now on the same coordinate system. That is the DQ0 reference frame. So then once we have these voltage expressions, we are having, you see the presence of lambda D, lambda Q, lambda 0, lambda FD, 1D, 1Q, and 2Q. So we'll be now trying to find out these lambda D, lambda Q, lambda zeros, okay? We already have them in lambda A, lambda B, and lambda C, okay? But because in 8A, B, and C, they are appearing as lambda D, lambda Q, and lambda 0, so we want the whole expression. So we want to use this expression of lambda A, B, and C, which we earlier had. So this is our original equation number 3, where we had this matrix, lambda ABC minus LSS IABC plus LSRI rotor. But we need them in the form of lambda D, lambda Q, and lambda 0. So what to do? We can write this again in the vector notation. So this is lambda A, lambda ABC. So what can we write? So we can write it, we can replace it simply by TDQ0 inverse, as we did in the last class, right? Minus LSS, then IABC, we can again write TDQ0 inverse, ID, IQ, and I0. Okay, plus LSR, then again TDQ0 inverse. Do we have to apply TDQ0 inverse there for these 4 currents?
No, sir.
No. So we simply leave with this, okay, because already they are in the DQ0 reference frame. So we don't have to bother about the conversion here. So it is I2Q. Now, if I want only this lambda D, lambda Q, lambda 0, what I have to do, I have to simply erase this and write it down here as a pre-multiplying matrix. So this will come as TDQ0. There was a minus sign, and here also you will have a TDQ0. So this LSR will be pre-multiplied by the TDQ0 matrix. Okay. So thus, from this ABC reference frame, we can come into the DQ0 reference frame. So let's see. So with this equation, we will be getting this. Okay, so you see whatever I wrote earlier with this green color, this is repeated here. So we have got the lambda D, lambda Q, and lambda 0, that is equals to minus TDQ0 LSS multiplied by the inverse of TDQ0 IDIQ I0 plus TDQ0 LSR into the currents. So then what you have to do, you have to calculate these things, minus TDQ0 LSS into TDQ0 inverse. Simply calculate it, simplify that. So you get these 3 by 3 matrix. And again, LSR, originally this LSR was space dependent or theta dependent. Let's go back to the LSR expression. So this is LSR. So you see, we have the presence of theta s everywhere for all these 12 elements inside this big matrix. So once we apply TDQ0 on these LSR, there will be some modification. And to our advantage, with this application of TDQ0 on LSR, we find that, well, now we only have to live with this theta independent terms, okay, LSFD, LS1D, LS1Q, LS2Q, and many other zeros present there. So we have to actually simplify this block to reach here and this block to reach here. And to our advantage, we see that, well, in none of these expressions inside these matrices, inductance matrices, we have the theta, okay, presence of theta. So we actually have achieved our target, okay. So we started the Parkes transformation with an aim that, well, if we apply the Parkes transformation, then hopefully we will get rid of the theta. So we see that, well, we don't have any theta left over here, okay. And these LAA0, LAAP, and LA0 plus LAAP and minus LAAP, these things are actually constants, okay. These are constants. And they are actually dependent on, if you remember, PD plus PQ over 2, there was some term like this, and PD minus PQ over 2, which were the permeances along the D axis and along the Q axis for the salient pole machine. So this PD plus PQ over 2 was LAA0, and LAAP was something like probably PD minus PQ over 2. Those are already present in the earlier slides of this lecture note, okay. So you can find them easily. So these are constants. LSFD, LS1D, these are again constants, okay. So all these are now constants and independent of theta. So with the application, or with the help of the Parkes transformation, we have got the advantage that we were looking for. So once we have this LD, we continue with some a little more modifications on these stator flux linkage equations. Remember, these lambda D, lambda Q, and lambda 0, these are related to the stator flux linkage. So now we see that, well, and in these positions, we have 3/2 LAA0 plus LAP and 3/2 LAA0 plus minus LAP. So what is this? This term, this first term is actually what? It is relating the flux linkage in the d-axis or along the d-axis and the corresponding current through the d-axis coils. So how can we write this? What is the relation between, what should we write here? What is the relation between lambda and I? How can we relate? Magnetic circuit basics. Any flux linkage and I. How can we relate? Anyone?
Number of coils into I.
Number of coils. Not exactly. That is MMF, ampere turns. Okay, that is MMF, number of turns present in the coil and the current through the turns. That is MMF. I'm not talking about MMF. I'm talking about the flux linkage. Anyone? What is d lambda over dt? Can anyone remember? Was it something like this? Can you recall now? Rate of change of flux linkage is L, can be represented by L di over dt. So if you cancel out the d by dt terms, what is left? Lambda equals Li. So simply this blank space should be filled up with some sort of inductance, right? Because the blank space is actually relating the d-axis current with the d-axis flux linkage. So simply we can write it as our LD. Is it okay? So lambda d is LDID. So that means whatever is here, we can replace it by some term known as LD, the d-axis inductance. Okay. What about the second term over here? What is it doing? It is actually relating the q-axis flux linkage and what? Which current?
IQ.
IQ. So you see there is no actually linking. Okay, d-axis is purely, d-axis flux linkage is purely depending upon the d-axis current. Q-axis flux linkage is purely dependent upon the q-axis current. Okay, so this is another benefit, as I mentioned in the last class, to keep lambda d and the d and q axis 90 degree apart, to assume that they are hypothetically placed 90 degree apart. So these are the additional advantages. You are getting many zeros. So while calculating the value, numeric values for lambda d, lambda q, etc., then you see you only have to think about this term. There is no linkage between d axis and q axis terms. Okay. So what about this then? So lambda q is again some function of IQ, and again this is purely linking q axis flux linkage with the q axis current. So we can simply write it as the q axis inductance. Okay. So ultimately what we have lambda d equals LDID, lambda q equals LQIQ. And what about lambda 0?
0, sir.
Lambda 0 is completely 0 because you see nothing. 0. No contribution under steady state. Okay. So we leave the lambda 0 for the time being. We will not continue with that because that will come up ultimately as 0. So lambda d also has some other terms actually, because there are two other coils present along the d-axis, remember? So these lambda d is actually, these lambda d, lambda q, lambda 0, they are some replaced variables out of the stator coil flux linkages, lambda a, b, c, right? So these d, this q, they are actually some transformed variables from the ABC frame. So other than these three, we also had actually the field current, the damper coil, number 1 along the D axis and damper coil 1 and 2 along the Q axis. So again, the lambda D would have some effect due to the flow of current in the field coil. So it would be IFD into LSFD. So IFD into LSFD plus I1D into LS1D. Similarly, you can write for lambda Q. Okay. Similarly, you can write for lambda Q. So with this, all this information, what we do, we say, well, you see what I have just mentioned, 3/2 LAA0 plus LAAP is my LD, and 3/2 LAA0 minus LAP is the LQ. And then we actually take up two components for these LD and LQ. What are the two components? These LD and LQ, respectively, they represent the total inductance along the D axis and the total inductance along the Q axis. If you look for the components of these inductances, then we can write that this total inductance, there will be some part of the inductance that will come from the mutual effect, and one part will be actually lost, and that inductance is represented by the leakage inductance. So among the total flux linkage, some flux will be coupled, mutually coupled, and some flux will be actually lost through leakage effect. Okay. So that's why we have to model these two effects, to include these two effects, or to show up these two effects in our modeling. We are actually decomposing the total LD into its two components. One is the mutual effect, another one is the leakage effect. And if we rewrite this to find out what is LMD, then simply LMD would be LD minus LLS. So this is how these two lines are actually obtained, these two relationships. LMD is LD minus LLS, and LMQ is LQ minus LLS. The original relationship is this. LD is LMD plus LLS, and LQ is LMQ. The QX is mutual inductance and the corresponding leakage inductance. However, we are assuming that, well, along the D axis and Q axis, we have equal values for the leakage inductances. Okay, this is one assumption. So with these definitions for LMD and LMQ, what we do, we simply rewrite our stator flux linkage equations in terms of the leakage effect and the mutual effect. Okay, so we are simply replacing LD by LMD plus LLS. So there was LD actually, lambda D was minus LD ID. So we are replacing LD by LLS plus LMD. And this LSFD is due to the linkage between IFD and the D axis coil. Okay, and LS1D is between the D axis transformed flux linkage and the D axis damper coil current. Similarly for the Q axis and for the zero axis. Okay, so next, for the rotor flux linkage, actually there is no change because we're not transforming anything in the rotor circuit. It's not required actually. So the rotor flux linkage remains as it was. So actually these 11A up to 11D, these are repetition of some previous expression of rotor flux linkage. So you can say those four expressions are simply the same as this. Okay. So lambda FD is minus LFD A IA plus LFD B IB LFD C IC. Of course, this LRS has to be transformed. This LRS, because not this LRS actually, this IAIB IC actually has to be transformed. Okay, with the help of the TDQ0. So we'll see that how to write this again, because probably that is skipped in this slide. So you can write it like minus LRS. Then how do you write IABC in terms of IDQ0? we need IDQ0 here, okay, because everything is transformed to DQ0 variable. So because in the first part of this lambda rotor, we have the IABC, presence of IABC. That means we have to transform this IABC into IDQ0. So how do you replace this IABC with the help of IDQ0?
TDQ inverse.
TDQ0 inverse, very good. So TDQ0 inverse, then IDQ0 vector plus what about the second part? What we have to do with iRotor? iRotors are already along the DQ axis, okay? Already along the DQ axis. So we don't have to bother. So we leave with iRotor as it is. So then if you multiply the LRS expression with the TQ0 inverse expression, then you will actually get the equations that are presented here, okay? 11A up to 11D, okay? So a little bit of manipulation is required there. It's not straightforward, specifically for getting this ID and IQs, okay? These four, IFD, I1D, IFD, I1D, I1Q, I2Q, they will remain same. This part will be unchanged. However, this part requires some little calculations. So we have got the stator flux linkage now for along the DQ axis, and the rotor flux linkage equations now along the DQ axis. Now what we see from here, there are some observations that whatever equations that we have got till now, all are in actual units, okay? We haven't yet applied any sort of per unitization. So one of the remaining target would be to consider the per unitization of all the equations that we had, okay? All the equations of interest, okay? That means all the equations that we have along the D and Q axis, we are going to apply the per unitization concept on those. And as you know, for getting the per unitized system out of the actual system, we need to define, first of all, some base quantities, okay? And among the base quantities, what are the base quantities? For any AC system, what are the base quantities? Similarly, for any DC system, what are the base quantities? If you want to convert an actual system into per unit system, AC system, what do we have? There are actually four things of interest, okay? One is the voltage, another one is the power, another one is the current, and another one is the impedance. So while defining the base, introducing the base, you have to start with any two out of these four. So that is to say, either you go for defining S and V and calculate the required bases for I and Z and continue with the per unitization conversion, or you take S and I or S and Z, whatever. That means if you take any two of these four, then the other two will automatically can be calculated, okay? So for this system, let's say we take base S as the MVA base for the synchronous machine, V as either KV or MV or V, whatever. Now, because this is a three-phase system, either you have to go for, okay, there's a three-phase system and AC system. So there are various ways in different books. They actually adopt different values for this base voltage specifically. For example, some might say, well, I will go for the peak value, okay, KV peak. Some will say, no, I will not go for peak, I will go for RMS. Some will say, well, I will go for line to line because it is three-phase. Some other will say, well, I will go for line to neutral. So there are these four possible variants for taking these V. Is it clear? What are the variations possible here? KV, V, or MV, it doesn't matter. It's not a big deal, but the changes, okay, changes throughout the conversion. It depends on whether you are taking the line to line quantities for the voltage or the line to neutral quantity for the voltage, So either you go for line to neutral or line to line, and either you go for peak or RMS. So these are the variants for taking the voltage bases for the AC side. Remember, the stator coils, they are carrying AC quantities, whereas the rotor side, it is containing the DC quantities, DC field excitation. So it's not like your undergrad level base conversion. Okay, transformer, you are converting there is transformer, there is generator, there is motor, there are loads. So all are basically AC system. Okay, so you simply go for only mentioning what is your AC base or what is your base for, let's say, the whole system base, and what is your whole system power base and whole system voltage base. And then depending on the transformer, you can simply calculate the voltage bases for the remaining part of the network. And again, if you take a common base for the whole system for the AC network, then it is pretty easy. Depending on the nameplate data or the rated data of each of the components, you can easily calculate the corresponding per unit values. Okay. However, in this case, for our system, we also have the presence of DC coils or DC voltages applied into the rotor coils. So that's why I mentioned that you have to take bases for the AC side quantities, and also you have to take the bases for the DC side quantities. Of course, in general, what we do, we take the power rating P base for the DC side to be numerically exactly equal to the S base here. Okay, just to make the calculation simpler. And the VDC and IDC will automatically come. And because there is no Z, so you will get simply RDC. Base, all these are bases. So I'm not going to cover actually this base conversion part. It is pretty straightforward. So if you want, you can go through the section where these base conversion part is actually covered in detail. Okay, in the book, the chapter that I have already, I think, shared in the Google Classroom, chapter 3. So in chapter 3, we'll find the detail of this part. But some of the introductory concepts I have just mentioned here in the lecture. For further understanding or further calculation, you just simply take help from the book section. Okay, the per unitization about base conversion. Okay, so our first target now, or the next target now, would be to get the equations in per units. And another thing that we are little concerned about is this. Okay, we have the mutual inductance for the stator side and for the rotor side, but we see that, well, they are not same. That is to say, if we look into the matrix now, very short time, let me erase this first. So in the stator circuit, the mutual inductance and the rotor circuit mutual inductance, we expect actually, for our ease of calculation, we expect them to be equal. But unfortunately here, we see that, you see LMD is the D-axis mutual inductance. LMQ is the Q-axis mutual inductance, and they are not same. We have, you see, LD minus LS, LQ minus LS. Rotor, what are the rotor mutual inductances? Okay, let me go through further or few more mutual inductances. This is one of the mutual inductances, LSFD. Between what? Between the stator coil S and field coil. So this LSFD is not the same as LS1D. You see, this is for D axis. Again, for Q axis, LS1Q, it is the mutual inductance between the stator coil and the 1Q coil. LS2Q, this is the mutual inductance between stator coil and the 2Q damper coil. Again, this LS1Q and LS2Q, they are not same. These are the observations for the stator flux linkage equation. Similarly, for the rotor flux linkage, you see LFDFD. This is, of course, the self one. So LSFD, again, this is the mutual between field winding and stator winding. FD1D, between field winding and 1D coil. And similarly, you can see if 1D, 1DFD, LSFD. So these are the mutual inductance values that are different till now. So let's see if we can get rid of this difference and we can bring them to the common ground or to some common expressions. That will make the equations look a lot simpler, okay, if we can make them equal somehow. So these are the two targets. Target number one next is to convert all the actual unit based equations into the corresponding per unit equations. That the detail I will not cover. You can take help of the book. But the final expression I will provide here, and the mutual inductances for the rotor circuit or in between the stator circuit coils and in between the rotor circuit coils are not same. So after the per unitization is done, okay, we come up with this. So you see from now on, you see that all the symbols are capitalized, okay. So this capitalization, you see capital V underscore subscript D, capital RS. On the other hand, the previous expressions, all the currents, you see ID, small letter, IQ, I1D, 1Q. So this change of notation is simply to signify the fact that now we are in per unit domain, okay. So the R is in per unitized form, I is in per unitized form, psi, it is now capital psi. So this is per unit flux linkage, okay. This is per unit flux linkage along the Q axis, per unit flux linkage along the D axis. So due to the per unitization steps, we see that we have the presence of this additional term here, 1 upon omega base for the expression of VD and 1 upon omega base for the expression of VQ. And actually the 1 upon omega base is there for all of these voltage equations, okay. However, the signs, you see the signs for the currents are unchanged. Of course, that is as expected. Even you apply the per unitization, you shouldn't expect that the current direction should change. So you see the stator current or the transformed stator currents from IABC to ID and IQ and I0, they are having a negative sign, whereas the rotor currents are still with the positive signs. Okay, so detail again, the detail of the per unit, it is again time consuming, and if you have interest further, then you can go through the article given in the book. Well, now we take, we group the D-axis flux linkages together, okay? We group the D-axis flux linkages together. So in the D-axis, we have 3 coils. One is the transformed variable, psi D. This is coming out of the psi A, psi B, and psi C, okay? This is the transformed variable. We're using the Parkes transformation, whereas psi FD and psi 1D was already there. This is the field winding flux linkage, and this is the damper winding 1 along the D-axis flux linkage. So again, this is per unitized, okay. That's why you see all inductances are even in capital, okay. Because remember, we had actually inductances earlier. We had L, okay, we had L's. So in the actual unit representation, we were dealing with small L's. On the per unit representation, we are having capital X. What is the relation between L and X? With the help of omega, we can relate them, right? Because, so this is L. So we were in L in actual units. In per unit, we are writing them as X. Why is this possible? Because 2 pi f is our base frequency. Okay, simply this is our base frequency. So simply we can say that, well, we are dividing this 2 pi fl by the base, so we can simply write x equals L. Okay, so using this relation, using the concept of base angular frequency, omega base, because in the AC system we also have to deal with the base frequency, that should be 2 pi f base. And of course the base frequency, depending on the country, mostly in our places we take 50 Hertz as our base frequency. So this is what they have taken. And thus in per unit, you have L, the inductance is the same as the inductive reactance, okay, in per unit. So that's why we can simply say, in place of else, after the per unit conversions, we can easily use the X notations. So we have, you see XD, XMD, and XMD. What is the benefit after per unitization? We see that, well, now the mutual inductances are same. You see, all the mutual inductances. So actually, with the help of power unitization, we can get rid of the dissimilarity of the inductances between the mutual circuits for the DXs. Okay. So you see, only changes are along the diagonal, whereas off diagonal elements are all the same. Okay. So psi d is now XD minus ID XD plus X MD ID IFD and X MD I1D. Okay. Similarly, psi FD and psi 1D. So this is what we actually wanted, and we have achieved it through the power unitization. So these three are outcome of equation 10A, 11A, and 11B, where the original expression was like this. So we are actually taking the actual unit representation of lambda d. This is one of the DX's flux linkage. What are the other two? We take lambda FD. This is residing on the DXs. Another one is lambda 1D. So we group them now. So previously in this slide, we were grouping the flux linkages like DX, stator flux linkage and rotor flux linkage. But later on, in equation 12, we are grouping, sorry, equation 13, we are grouping them like DX's flux linkage, where we see that now the mutual inductances or mutual reactances are exactly same for all the circuits. And similarly, we are grouping the Q-axis flux linkages. So one of the Q-axis flux linkage is coming due to the Parkes transformation from the stator flux linkages, ABC frame. The other two are the damper coils, psi 1Q and psi 2Q. And again, here we see that all these mutual inductances or mutual inductive reactances are exactly same. Okay. So this is the added advantage of power unitization. So with that, now we have expressed the flux linkages. We have got rid of the unequal or imbalance between the inductances. Now we are actually done with the, tedious part of the calculations. Okay. So now we will slowly we will be going to our target. That target was to build up the third order dynamic model, if you remember. Okay, the third order dynamic model for the synchronous generator, third order dynamic model. So we actually started from 2.2. Remember, our model was 2.2. Okay, 2 coils in the D axis and 2 coils in the Q axis. But now after simplification, we will be left with only the field winding, dynamics out of the machine. So all the damper coil effects will be ignored. All the damper coil effects will be ignored to reach at this model. Okay, the third order model. But the most common one used in practice in industry or industrial software, even the industries where they use the simulation models. Okay, simulation models for simulating different dynamics associated with their plant. The commercial softwares, they mostly use the model 2.2. Okay, they mostly use the model 2.2. So for the time being, we understand actually what is the background behind 2.2, development of the model 2.2. Okay, but for our course, we will take a simpler model. Okay, but we have to understand that this 2.2, we already know what is in the back door. Okay, what is there, how we reach there at the model 2.2. However, for further calculations in this course, we will be focusing on third order model. Okay, so now let's see how we can reach from the 2.2 model to our desired third order dynamic model, which is also known as the flux decay model. Okay, flux decay model. So for reaching from the 2.2 to our desired third order model, we have to go through some simplification steps. So let's go through those steps. So the first simplification is we ignore the effects of damper windings. We ignore the effects of we ignored the effects of damper windings. So no damper windings. And we also said earlier, and that stays also, that it stays for the future steps, that we are still considering that we have a balanced system. So if we have a balanced system, then what do we get? We get this part is equals to 0, because in the balanced system, you don't have any zero component current. And of course, this d psi over dt, this under steady state, this will be 0. And the main thing is that V0 will be 0. There is no zero component voltage also. So this 12C we will not use anymore. If you get rid of the damper windings, which equations will be vanished from here, from this set? If we get rid of damper windings or damper coils altogether,
12 EFG.
12 EFG, excellent. So these three are related with the damper coils. So these three we will not assume anymore. However, if we want to live with 2.2 model, then already you have reached the dynamic model. Okay, this is the dynamic model for representing 2.2, except this, because this is, I mean, considering balance system, this will not be there. So equation 12A, B, along with D, E, F, G, this is the dynamic model for representing 2.2. Okay, clear? And from here, you can increase it, you can decrease it. Like if you look for 3.3, then what you have to do? If you look for the model 3.3, then there will be some additional states. There will be some additional dynamic equations, right? There will be one more equation in the d-axis, and there will be one more equation in the q-axis. Here will be the changes. If you are looking for 1.1, then what you do? So if it is 1.1 model, then which part of this will be erased? Can you erase VD and VQ for any of the models? Either it is 3, whether it is 3.3 or 2.2 or 1.1?
No, sir.
No, because these are related with the stator coils. You can't get rid of this. These are always there. So VD, VQ will be always there. Considering a balanced system, these 12C will never be there. Okay, considering a balanced system. So we get rid of these all the time. This VFD will always be there. This is the field winding. So 12A, B, and D will always be there. The changes will be here. Changes will be here. If the model order increases, then you have to add up few more equations here. If the model order decreases, you have to reduce some of the equations here intelligently. First of all, you have to think of the physical presence of the coils of the model, and then you can easily write down the equations with the help of this derivation. So that's why this 2.2, we took this 2.2 as the example. You can increase the dynamics of the model, you can decrease the dynamics of the model pretty easily from this. So our target for this course is to reduce the model size. So we get rid of all the damper coil dynamics and equations. That means with our model, we are not actually going to see the effects of the damper coil dynamics. Okay, that is not possible with our model. So this is one of the limitations of our model that we are going to use in this course. But you know that 2.2 you have already developed. This is 2.2. All these 12.A to 12.G without 12.C. This is your model 2.2. So now we reduce the size. So after these simplifying assumptions, we will be left with what? We will be left with 12A due to the stator coil, 12B again due to the stator coil, and VFD due to the field coil. So these three equations will remain. So now we will just rearrange those three equations. Okay, I said about three equations. Now we will rearrange those three equations. And those three equations were related to which voltages? Those were related with VD, okay, present in 15A, then VQ present in 15B, and VFD present in 15C. So simply what we are doing, we are taking the differential term on one side of the equation just to make the coefficient of these differential terms equals to 1. Okay, that's why we are simply changing the sides and rearranging the equations 12A, 12B, and 12, probably 12D. Okay, 12A, 12B, and 12D. Simply we are taking omega base on this side, this thing on the other side, making d psi d over dt with a coefficient equals to 1. Similarly for d psi q over dt with a coefficient equals to 1, and d psi fd over dt with a coefficient equals to 1, and taking everything on the other side. So we are left with 3 equations there, 3 dynamic equations. Okay, but we are not done yet. Okay, we are not done yet. So let's see what else is left to reach at the third order model. Next, what we do, we ignore few more transients or few more dynamics from our model to reach at the third order model. We ignore these dynamics, okay, d psi d over dt and d psi q over dt. These are known as the stator transients, and they are very fast, means their frequency range is much higher than the frequency of our interest. Now let me tell you what is our frequency of interest. The frequency of interest for our modeling, we will call them as low frequency. Compared to what? Of course, compared to our base frequency, 50 Hertz. So this is our base frequency. The model that we are going to develop, our target in this course, in few of the targets, one of the few targets is to analyze the low frequency oscillation. The low frequency oscillation. So the low frequency oscillation actually lies or is actually linked up with very low frequency, 0.5 to 1.5 Hertz. Whereas these fast transients, stator transients, these are linked with 50 Hertz or more, even higher frequency. So because we are interested on a different frequency zone, we want to see the dynamics of the machine on a different frequency zone than these two. So we are going to neglect these dynamics. Okay. For some other phenomena, for studying some other phenomena, like one of the example could be studying the SSR or subsynchronous resonance, or maybe some other high order dynamics, okay, high order or high frequency dynamics. If you want to study the high frequency dynamics, then you cannot ignore these terms. But for our course, or one of the target is to study the low frequency oscillation. Okay, so that's why we are not interested in high frequency oscillation. Rather, we will be interested in this range, 0.5 Hertz to 1.5 Hertz, or maybe 2 Hertz, okay, in this small frequency zone. So that's why we are going to neglect these two terms altogether. However, for high frequency phenomena, studying high frequency phenomena, we cannot ignore these two. Okay. And one example of the high frequency phenomena, as I mentioned, this is SSR or subsynchronous resonance. So with this assumption of neglecting this d psi d over dt and d psi q over dt, what do we get? You simply equate this to 0. Okay, equate this to 0. So what is left? The 0 divided by omega base. If you take it to the other side, so you're only left with this VD equals to minus RSID minus omega psi q, and VQ equals to omega psi d minus RSIQ. However, we are also neglecting another thing, that is the armature resistance. Okay, so the armature coil inductance and armature coil resistance in general, while we design the machine, in general, these values are kept to a very, smaller proportion, kept to a very small proportion of the armature coil reactance or armature coil inductance. Can you say why? Let's say you are designing the generator coils, okay, 3-phase coils. In general, there is in the coil, let's say this is phase A, RA, LA. And similarly, there are other 2 phases. So if you are a designer of the generator, okay, why is this followed? Can you tell the reason? So S means it can be A, B, or C. Okay, phase A, phase stator. S means stator. So it can be coil A, coil B, or coil C. So for all the 3-phase coils, we generally tend to design the coils in such a way that this RS value is much, much smaller than the corresponding inductance values. Why? No one. Oh, this is basics.
Power loss is less.
Yeah, actually we don't want real power loss, right? We're producing power after so much effort, after burning the fuel, heating the water, using the boiler, creating steam. If I go for conventional system, okay, running the turbine, producing through the using the steam, then running the turbine, steam turbine, coupling the generator, ultimately getting some power. Then after producing the power, let's say the 3-phase power, if you are supplying it through some coil where you have significant resistance, what will happen? The whatever power you generate and whatever power you transfer through this phase, let's say PA, up to the load end, some of your power or significant amount of your power will be actually lost, real power, right?
Yes,
so
sir.
that's why you don't want this RS to be of the same size or same dimension or same value as XS. So intentionally we keep, while we design, actually we can't make it exactly 0 because there is no ideal coil in real world. So there would be some R, but that R should be kept to a minimum. So that's why this armature resistance, neglecting this armature resistance is a valid assumption, okay? Because in general, RS is very, very less than the XS. So if we neglect RS, then what will happen? This term will be 0. Considering the fast transients, this will be 0, this will be 0, this will come here 1 upon omega base, so multiplied by 0. This will come here 1 upon omega base multiplied by 0. So ultimately you have VD related with omega psi q, VD equals to minus omega psi q, and VQ equals omega psi D, right? And the third one is the field circuit dynamics. The field circuit dynamics will be obtained later on. We'll model it. We'll model it how we are going to achieve these dynamics. So for getting these dynamics available to us, for having these dynamics, we have to go through the model later on. We will do this. We have to go through the excitation system modeling. Okay, that's the next target. We are doing the generator part now. Later on, we will go through the excitation system. That excitation system will give us this d psi FD over dt, this psi FD and its variation. Okay. If you don't have excitation system, if you don't include it, then actually you reach at your swing equation model or classical model. So actually with the inclusion of these excitation system dynamics, we are having our third order model. So this is our third dynamic equation along with the previous two. Remember what were the previous two? The first one was d delta over dt. The second one was, this is from the swing equation topic. The second dynamic was the angular motion or angular speed. The first one was angular position. Then second one is angular speed. The third one is related with the excitation system dynamics or field coil dynamics. So this is our third order model. Okay. Order number 1, order number 2, and order number 3. So, and the other two, you see these are vanished. So these are going to 0. We are neglecting them. We are neglecting them. So that's why this model is called as the third order model, third order dynamic model for the synchronous machine. So with all these assumptions, we are left with equation 16a, b, and c. Where the 16c is the same as 15c. There is no change. Only 15a and b are transformed like this with the applied assumptions. So now a little bit more simplifications. Some are notational, some are again conceptual. One of the conceptual assumption is that because this omega that is coming here, this omega, because we are talking that we're telling that, well, our main interest in this course, one of the main interest is to look at the low frequency oscillation. Okay. To have the low frequency oscillation, the result of the low frequency oscillation can be achieved after we go for the development of some small signal model. Okay. Through linearization. That can be achieved only through some linearization. We'll take it later on. Okay. Linearization. So because we will be going for studying in detail the small signal model, that will help us to study this low frequency oscillation problem. So because of this small signal model, small signal means what? Small signal means you are applying some small disturbance to your dynamic system and you are looking at the response. So because this omega is one of your state variable, remember, omega is one of your state variable, one of your variable, dynamic variable. So this, when we say small variation, so that means we will be looking at some small change in omega, right? We're not looking at the large excursion of omega from the equilibrium. So this omega, the change in omega would be very small for our model that we are interested on. So that's why for this small disturbance model, this omega original value can be written as actually omega naught plus del omega, where omega naught is the steady state value and del omega is nothing but, this is del omega. Del omega is nothing but deviation of omega from its steady state value. Because it is a small signal model, so we expect this del omega to be very much near or very much near to 0. Okay, very much near to 0, but not exactly 0. It is very much near to 0. It is pretty small. So that's why, what is this omega naught? Omega naught is our base value. In per unit, it is 1 per unit. So this omega is assumed to be approximated equal to, assumed to be 1 per unit. But this assumption is only valid for a small disturbance model. Remember, for a small disturbance model. This is not valid for large disturbance model. This is only valid for small disturbance model. So with this assumption, we again get rid of this omega. We had the omega here. We had the omega here. That is assumed to be almost equals to 1. So we have Vd equals to minus psi q and Vq equals to psi d. So life is getting simpler slowly. After all these tedious calculation, Parkes transformation, per unitization, permeance calculation, after all these efforts, we are slowly going into something to cherish, okay? Something to be happy with. So Vd is minus psi q, Vq is psi d. And now we will go for some notational simplifications. Why? Because you will see these notational simplifications in the commercial software or in the research paper or even in the book. The final model that they use some notations, we will be trying to reach up to those notations. Okay. So for that, what we do, we assume some notational simplifications now. So we assume that there's a variable EQ dash, which is xmd over xfd multiplied by psi fd. Okay. We have some other EQ. So what is this EQ dash? How do you call it? So we call it basically The Q axis voltage, E stands for some voltage, Q axis voltage in transient condition. The dash stands, single dash stands for transient, double dash stands for subtransient. So EQ dash means it is the voltage, the synchronous machine voltage along the Q axis under transient condition. Okay, and that is related to the field axis flux linkage, the field flux linkage. Okay, so that is a function of field flux linkage and a proportion of some proportion of your XFD. What is EQ? If EQ dash is the transient form of voltage along the Q axis, EQ is the steady state form of the voltage along the Q axis. And that is again a function of IFD and XMD. And what is EFD? EFD is nothing but a function of the original or actually applied field voltage. Okay, this is the actually applied field voltage. And this is some transformed field voltage from transform notation of field voltage, EFD. So in the literature, in the research papers, in the softwares, commercial softwares, you will not see actually SHI-FD, IFD, or VFD. Rather, you will see these things: EQ, EQ dash, and EFD mostly. So that's why we are going for these simplifications. Okay. So then what we do for representing our equations in the simplified form or with the help of these notations, we do what we actually multiply equation 16c by this term, and then we get this. Where you see a dot over EQ dash, this dot is nothing but the differential operator, time differential operator. So that means it is TD prime d over dt EQ dash equals EFD minus EQ. Where TDO dash, it has a name, of course. This TDO dash, the T means it is a time constant. D, it is the D axis time constant. O, it is the open circuit time constant. And this dash means it is the transient period. So it is the D axis open circuit transient time constant. And that is this, okay? XFD over omega base RFD. Okay, we continue with the simplifications because we are ignoring the damper coils. Remember, we are ignoring the damper coils. So our flux linkage expressions will also be affected. Okay, if you go to equation number 13, then we see what sort of simplification we are looking for. So if we ignore the damper coil, which of these terms will vanish? Which of these terms will vanish? From this column, which will be vanished?
SHI-1D.
SHI-1D, excellent. From this matrix, what will be vanished? Okay, come to this later on. First, what will be vanished from this column?
I1D.
I1D. So that means the terms coupling these two will be vanished. Okay, because we'll be living with these two sized vectors. Okay, 2 by 1. Only SHI-D and SHI-FD, you'll be left with this, and we'll be left with only these two currents minus ID and IFD. So what should be the dimension of this? Should be also 2 by 2. Okay, so you'll be left with only this XD, XMD, XMD, and XFD. What about the Q axis flux linkage? Which of these will be again vanished?
SHI-2Q.
SHI-2Q, okay.
SHI-1Q also.
SHI-1Q and SHI-2Q. So we will be only left with this. So this, and this. So we'll be only left with SHI-Q, XQ, and minus IQ.
Minus I.
So with this simplification, we actually get this equation number 19 and 20 respectively. Okay. With these simplifications, we are almost done. We have probably 1 or 2 slides before we go for some mathematical calculations. Till now, these are derivations. So then we will go for some phasor diagrams, and then we will be going for slowly to some mathematical calculations or math problems or example problems. Now we equate. So you see, we have one expression of SHI-D here out of equation 19. Okay, that would be minus XDID plus XMD IFD. And we have another equation of psi d. So we are equating, yeah, 17a and 20 first. Okay, let's take it first. So 17a and 20. So what is 17a? 17a, you see there is a psi q. Okay, minus psi q. And 20, what do we have? We have psi q. So that means we can relate this xq iq from 20 with vd from 17a. So that means vd is xq iq. And again, we relate 17b with the first equation of 19. So that means 17b, what is there? 17b, we have expression of vq, which is actually psi d. And again, here we have psi d, which is minus xdid and xmd ifd. So we equate them. vq equals psi d equals minus xdid plus xmd ifd. And this one is now written in terms of eq. Remember, eq is xmd ifd. So you see, we are getting rid of this term xmd ifd, and we are replacing it with our notational simplified notation eq. So we have vq equals, so our final equation of interest is this: vd is xqiq and vq is eq minus xdid. So these two we will carry on forward. Okay, we'll no longer use this psi q and psi d. We'll be leaving with vd, iq, and vq and eq id, these things. Now we try to establish relation between eq dash and eq, because one is in the transient state and one, they're same, the qx is voltages, but one during the steady state and one during the transient state. So we try to relate them. So we use some earlier assumption here. We earlier assumed this eq dash is xmd over xfd psi fd, and we use the expression of psi fd from 19. So you see this was unused, so we use it now. Psi fd is minus id xmd and xfd ifd. So using this expression and some notational simplifications, we reach, so you see we have, after we calculate this, we have xmd ifd, and that is eq. Okay, and xmd square over xfd, this is actually replaced by some function of xd dash. Okay, and where xd dash is a function of xd and this term xmd square over xfd. Why we are bringing this xd dash and xd? Remember, these values, when we buy a machine, they will provide you a catalog. They have some data in their catalog. So these are the part of the dynamic data. So in the catalog, you will see the presence of xd and xd dash. They will not provide you xmd, xfd, or etc. Okay, that's why we are using these simplifying notations. Okay, so you can directly read the data from the catalog. You can directly use these data available in the commercial software. You can use this data available in the literature, in the research papers, earlier works, in the books. So that's why we are actually converting everything to the notations that we will find in practical or real life. Okay, so that's why we are bringing xd dash. What is the xd dash? Again, xd is the d-axis reactance. So xd dash should be what? Dx is transient reactance. Dx is transient reactance. So then we use equation 18 and 23, and we finally get the third dynamics in terms of eq dash prime dot. There is a dot. This is dynamic equation. So this is our third equation. And now after combining this third dynamic equation with our previously derived classical model or swing equation model, we have our flux decay model or the third order model. So these two, the first two, they were already derived earlier. And after the end of the discussion for this slide, we are actually getting this eq dash equals 1 upon TDO prime is EFD minus EQ dash minus XD minus XD dash into ID. And in the next class, inshallah, we will, this is the model that we are looking after. So we're looking for, so we have got that model. Now we will continue our, let's say, calculation phase for this developed model. Okay. So whatever we discussed till now, starting from second week. First week we covered only actually the classical model. Second week we started actually this slide, synchronous machine modeling. So this was the target. We, after all this discussion, all this part unitization and all these things, we were looking for this third state equation or this third dynamic equation here. Okay. Of course, there are some algebraic equations along with this, and the algebraic equations are this equation number 21 and 22. So these are the algebraic equations. VD equals XQIQ and VQ equals EQ minus XDID. Okay, so any question? Any question?
No, sir.
No, not yet. Okay, so then let's quit here. Let's stop for today, and inshallah we will meet again in the next week. So till then, stay safe. Okay, assalamu alaikum.